Okay, so today we're going to start talking about the BRMS package. Before we can actually talk about that or anything else, have to talk about the fact that as an employee of Columbia and you being listening to this presentation, the fact that Columbia is seeking grants to develop STAN, has already gotten a bunch of grants to develop STAN, and the fact that actually use STAN to try to make money outside of Columbia presents the appearance of a conflict of interest that you should be aware of for listening to the rest of this presentation, which, like I said, is more focused on BRMS, which is our package that uses STAN to estimate the parameters of posterior distributions that you define during using our syntax. I have to say the disclosure because, you know, STAN and all that, and the fact that BRMS utilizes STAN to do its estimation, but I wasn't actually involved at all in creating the BRMS package. That doesn't change anything about the conflict of interest, but I didn't have anything to do with it. It was actually done by Paul Berkner when he was a graduate student. He's in Germany and has been continuing to work on this since he graduated. But when he started it, it was just basically his dissertation to create BRMS, which allows you to estimate a lot of models using STAN, but again, almost entirely just specifying our syntax to characterize the posterior distribution that you're estimating from, so you don't really have to write any STAN code yourself, although BRMS is taking that R syntax and generating a STAN program that it then compiles and samples from. And so the fact that it's creating these STAN programs locally once you enter your R syntax means that it can estimate a whole bunch of models. You can go for, you know, a long time really without, and, you know, being estimating Bayesian stuff without needing to go beyond what is already supported in the BRMS package. Now we're going to learn a little bit how to go beyond that starting in a few weeks, but for a couple weeks, and, you know, for longer than that if we wanted to, we could get by just using BRMS. It's that flexible in how much, how many different models it can generate STAN code for, probably hundreds, maybe 1,000, depending on how you count, although the lines between different models get blurry when you start talking about estimating these from a Bayesian perspective. But just because you can estimate like 500 different models or whatever in using BRMS doesn't, I mean, you should learn how to do those sorts of things, but you just don't walk into it and start using BRMS the same way that you would use like Stata or whatever. You have to understand the models that you're estimating, and basically understanding is demonstrated when you can draw from the prior predictive distribution of one of these models. Now, until you can do that, you have not demonstrated to yourself or anyone else that you understand what this model entails. And you have to understand what these models entail in order to have a chance of choosing reasonable priors for the unknown parameters in the model, the exogenous unknowns that you're trying to get the posterior distribution of. And if you don't have a thorough understanding of what the model is, there's no way you can specify before seeing the data what values of the parameters in that model would be, you know, more likely, less likely, what would be the median, what would be the mean, things like that. There's all kinds of people out there using quantitative methods that have, you know, so little sense as to what the model entails, or it's not even a generative model for the data generating process in the first place, that they would be, extraordinarily hard pressed and probably find it impossible to say, what would be reasonable values of the parameters, the coefficients, other sorts of unknowns for a model like that, because they don't even really understand the connection between each of the unknowns and, all the parts of the model. So if you ask someone, doing the typical sorts of things these days, just like throw random forests with a bunch of predictors at some outcome, one, you never see the parameters that are being estimated. But even if you dug in and found them, there would be no interpretation or anything like that by which you could say this would be reasonable value for the parameter, or something like this would be unreasonable. But if you think about things from a data generative process, you're drawing from the prior predictive distribution of the model that you think holds, then you can look and see, well, is what's coming out of this prior predictive distribution look like what I anticipate the outcomes will look like before I go collect the data? And once you've achieved that, then your priors are at least admissible. They could be, reasonably plausible priors for the parameters in that model. And once you've made it that far, then you could say, I understand this model well enough to estimate the parameters from it when I collect data from the wild to condition on. But you can't just jump to, estimating the posterior distribution immediately, because when you condition on data from the wild, there's all this stuff that, goes into the model, plus the additional possibility, which is not small, that the data that you've collected from the wild wasn't actually generated by the model. And so there's going to be a discrepancy there that's going to hopefully show up in like posterior predictive checks and whatever. But all that is layered on understanding or lack thereof of the model. This idea, well, maybe the data wasn't actually generated by the model. You need a different model. And then you could be, going back to square one. But when you're going back to square one or starting at square one for the first time, need to be having a good understanding of what all these models entail. And that's something that we're going to, continue to emphasize, even when doing models that are relatively easy to specify the syntax for, using things like brms or rstanarm or like 60 other R packages that are on CRAN that are using Stan to do the estimation in one way or another. So I think I said this before, but the basic workflow for Stan from R, when you're not using something like rstanarm, is writing the program in a Stan file with the syntax that gets, defines the posterior log kernel that you're trying to draw from the posterior distribution of, and this all gets translated to C++ and compiled. Now, when we do stuff with rstanarm, those Stan programs were already written, but they were written by hand, and they come to you, if you're not using Linux, from CRAN already compiled. What brms is doing is sort of making it easier to do step one and sort of doing step one on the scenes. So it will generate a Stan file in the temporary directory from the R syntax that you give it, and the R syntax that you give it is mostly similar to the syntax for rstanarm or other functions in R that fit models using frequentist estimation techniques. There's some extensions to the syntax that we'll talk about as we go on, but the fundamental difference between brms and rstanarm is that it's generating a Stan program locally based on the R syntax that you tell it, and that gives it the flexibility to cover many more types of regression models that can be put into rstanarm in advance. The sort of thing that requires more sophistication on the part of a brms user is that when you piece together one of these stand programs via BRMS, specifying the priors, the data, the family, all sorts of things like that, no one has really checked that the priors go together well or go together with the parameters in the model. And that's something that's a bit less likely to be a problem if you're estimating a model with BRMS, because those models were written by hand. They've been tested. Lots of people have done those same models with the limited choices of priors that are supported in RStan ARM. In addition to having lots of different families, so you can do lots of different forms of priors with BRMS, and it's entirely possible that no one or not that many people have ever used this combination of priors with this likelihood or for the model that you're specifying. And so you have to do more understanding of the model and more checking that those priors are reasonable, and you may get more problematic behavior in terms of divergences and things like that, because the settings and whatnot are different than those being used by RStan ARM that tries to eliminate some of those problems for you. Anyway, once you have this stan file generated as text, whether you wrote it by hand or you got it from somebody else or BRMS generated it for you, then you execute the binary that was compiled from the C++. And in the BRMS package, there's basically one primary function called BRM, which does that along with everything behind the scenes in step one. And then you get draws from the posterior distribution. And at that point, it's mostly like using RStan ARM or anything else. You have to diagnose problems. You have to analyze the results. You can make predictions for future data, things like that. But at least conceptually, that's all the same as the sorts of things that we've been doing before in RStan ARM. And moreover, it's a lot of the same functions you can call on objects produced by BRM as you can for something that is estimated by RStan ARM, one of the stan GLM or something like that. So questions about the differences here, right? So you'll notice when you call something with BRM, it'll pop up a message by default saying like compiling C++ model, and then it'll be like 30 seconds before it even starts to sample. That 30 seconds, it didn't have anything better to do, but that is sort of skipped when you do something from RStan ARM because the model's already come precompiled. So this figure from the reading, can't quite see the bottom of it, but anyway, the user specifies all the model information as R syntax when calling the BRM function. That is could be a lot of things, but it is primarily a R formula, a data frame containing all the variables referenced in the R formula, family that basically specifies what likelihood function to use, and prior, which is the prior on all the parameters in that model. The BRM function internally is going to call make stand code and make stand data. Those functions are actually exposed, and so when we learn a little bit more about how to write stand programs, we'll refer back to the stand code that is generated by BRM. It's a pretty good way to learn how to write stand programs yourself by looking at the stand programs that are generated for BRM for a model that you understand. And so more so than RStan ARM, where the stand programs are written by hand, but they were written in a way that is not really intended to be readily understood by people, even though it can be understood by computers. BRM has more human readability to the stand programs that it generates. It's been getting a little bit less readable as the stand programs have gotten more and more optimized and more general, but it's still something that you can read and learn from. But frankly, the stand programs that are sort of auto-generated by BRM are better than what most people could write by hand. And we see all kinds of questions on the stand, discourse every day. People trying to do their own RSTAN program, and they're like, well, I just want to learn. And they're learning, but in the process of learning, they're writing stand programs that are sort of worse than can be automatically generated by BRM. And so if the results were important, it would be better for those people to be using BRM in the first place. But the best of all worlds would be, you learn. One, you have a thorough understanding of the model, so you can understand the stand program that BRM generates for it. But you also have, enough understanding of what BRM is doing, what the stand language is, all about, and to where you can get yourself up to the level where you can write stand programs yourself by hand that are as good as what can be auto-generated by BRM, and you can push it beyond the set of models that BRM supports, even though that's surely in the hundreds. The make stand code function will make stand code and pass that on to the functions that compile it and whatnot in RSTAN. Also, the make stand data will produce the list of data that needs to be passed to stand. And this is something that is a bit tedious, but a lot of the people that have difficulty writing programs themselves in stand or getting them to even start sampling is just, how can I manipulate the data so that it's ready to be created in stand? And what BRMS has a relatively sophisticated capability of doing. What RSTAN ARM is doing is basically just generating a lot of matrices and vectors from the data frame that you give it and the formula that you specify to be the data structures that are being passed to stand. And that is something that should be able to do yourself, but a lot of people get tripped up just by making things the right size and the right format and stuff like that. So that is handled all fairly automatically by the make stand data function, which is going to be, it is exposed, but it's being called internally by the BRM function. And then the results, the draws from the posterior distribution come back from stand. There's a little bit of post-processing of those by BRMS in terms of formatting it for the summaries and things like that. And then the results can be investigated with shiny stand or predictions with posterior predict. There's some additional plots that BRMS is capable of producing and things like that. But basically, the value added of BRM is that it's more or less possible to combine all the steps except the last one really into a single call to the BRM function, which does all of this for you. But if you don't have any of the model that it's estimating, then BRM can do what you tell it to, but that may not be something that is scientifically or otherwise substantively worthwhile. Questions about this? So what are the arguments to BRM? There is a lot of them. That's in part because essentially all the functions in the or all the models that BRM can estimate go through this one function, whereas in RSTAN ARM we split it up into stand_ln and stand_gln and stand_ a bunch of other things. With BRMS, it's all going through one function called BRM, and consequently it's going to have to take a lot of arguments potentially, but most of these you wouldn't have to specify in any particular situation. The main ones that you are going to have to specify are formula, which, like I said, is a more or less regular R formula, although there's some extensions to the syntax to it. Data, which is a data frame containing all the variables referred to by formula. Family, which is basically what likelihood function to use, and prior, which specifies your priors. We'll talk about the function to do that over the next few slides. And then there's a bunch of other things that are either rarely needed, only pertain to particular models, have to do with what gets saved and what gets thrown away, and some other things that are honestly just not that great idea, like mean field estimation. Don't do that. Anyway, so we'll talk about these when necessary. One of the things that we won't specifically talk about today, but it's important, is this sample underscore prior argument. So that can be no, yes, or only. Only corresponds to like prior PD being true in RStanArm. It will write this stan program, it'll compile, but it won't condition on the outcomes. And so you're just drawing from the prior distribution. You can use that to make prior predictions in order to make sure that the priors that you're using are reasonable. I guess if you specify yes, it'll come back both drawing from the prior and the posterior in separate pieces. But the default is no, which is to just draw from the posterior distribution defined by formula, data, family, and prior. So if we need any of these other ones, we will refer to those arguments as we go. The more tricky one, and the one that's more different from how it's done in RStanArm, is the prior argument. So the formula argument to BRM, basically like a regular R formula, everything to the right of the tilde sign would be pretty similar to stan GLM in RStanArm, or other sorts of R packages. In many cases, the thing on the left of the tilde sign would be the outcome variable, but BRM has some extensions to regular R syntax for the left-hand side, well, the right-hand side too, but we won't talk about that this week. But extensions to the formula syntax to the left-hand side of a tilde and a formula, things like y, vertical bar, function of some variable. And the functions that I know of that you can use are sense and trunc to specify observations that are censored or truncated. There's weights and dispersion. Those are things that are more used when not doing MCMC. They don't exactly make sense. SE is for specifying so-called known standard error estimates in what are known as meta-analyses. These things are fairly popular in psychology, which is where Paul got his PhD. So trying to support the sorts of model that his colleagues estimate a lot. You don't see meta-analysis being done that much in political science or economics, but it's this idea, if you have like a bunch of studies ostensibly of the same phenomenon, they all have these estimates and all have these estimated standard errors. Could you do sort of literally a meta-analysis, a analysis of the studies rather than analysis of the underlying data, to get at sort of a posterior distribution for overall conclusion? Again, if you have all the underlying data, there's better ways of doing it, but a lot of times you don't, or people don't make their data publicly available, and so you just have to sort of take it from the published results in their papers. Another function that can be specified in some cases is trials. So if you're doing a binomial model, y would be the number of successes vertical bar, trials, and then give some other variable in there, number of successes out of this or that many trials in binomial models, and cat, which is to specify categories for ordinal models. We'll talk about more ordinal models more on Thursday. It's one of the areas where BRMS really shines in its support for handling models with ordinal variables, whether that's outcomes or predictors. So we'll talk about that more then. So there's some other functions that you can put to the right of a vertical bar and to the left of a tilde when specifying the formulas. But for the most part, these formulas are the same as in R_arm and in R generally. There are some other differences that come up occasionally, but we'll learn about those more when we get to them. Questions about this? So the family argument to the BRM function is basically just specifying the likelihood. It probably would have been better had it just been called likelihood. Family is the name of the argument used in the GLM function and consequently in the stand GLM function, but it really only makes sense to think of that as a family if the likelihood is within the exponential family of distributions, which includes, you know, the normal and the exponential and Bernoulli and things like that. But you can also estimate models in STAN and BRMS just as well with likelihood functions that are not in the exponential family, such as student t or things like that. So anyway, all of these can be passed to the family argument, but really they just indicate the likelihood function. And there's a ton of likelihood functions that you could use. And these are just most, but maybe not even all, of the likelihood functions that you could specify in the STAN program if you were to write it by hand. So certainly, you know, Gaussian student t distribution, Bernoulli binomial. Bernoulli is just a special case of binomial, but if your outcomes are literally zeros and ones as opposed to counts of Bernoulli models, it can be more efficient to specify Bernoulli as the family rather than binomial with trials equal 1. Negative binomial, which we talked a little bit about. Some other ones, distributions we haven't talked about, like, you know, inverse Gaussian. That's almost never used, but you can do it in BRMS. And a bunch of other things, some of which we will talk about today, others of which we will talk about future sessions, but some of these things we're just not going to have time to talk about because there are so, you know, many of them that can be specified. And these are just the different likelihoods. When you combine this with, you know, all the different priors and all the different things that you can do with structuring of multi-level data or, you know, nonlinear functions, like I said, you really can do hundreds, if not 1,000 different models just through the BRM function. So you can specify any of those as your likelihood. The prior argument to BRM is basically a glorified list that is produced by a call to the set prior function in BRM, which has the following arguments. Prior, which is a character string naming a variable and any of its hyperparameters in the STAN language. So if you call set prior, that needs to be in quotes. So if you do like quote normal 0.5, that's saying, you know, the prior on whatever this pertains to is a normal distribution with a mean of 0 and a standard deviation of 5. This needs to be in the STAN syntax, so using the STAN names for those distribution as opposed to the R names, and using the STAN parameterizations as opposed to the R parameterizations where those differ. But in the case of a normal, both stan and have the same parameterization, although you just spell out the word normal rather than like denorm or whatever like you would do in R. The class argument indicates what parameter this call to set prior pertains to. We'll talk about more on the next slide about this, but like you might say, okay, this is the prior that pertains to the regression coefficients. But in BRM, you can estimate so many different sorts of models that there's different classes of parameters. And so you can have like multi-level models, all sorts of things going on. The class variable indicates the BRM, or the class argument indicates what your call to set prior is talking about. CoF is a perhaps misnamed thing. It really only is a CoF when class is B, indicating you're talking about regression coefficients. But if you have multiple regression coefficients, you can say, well, this prior pertains to the first the regression coefficient on the first variable, whatever that is. And then another call to set prior pertains to the second coefficient. And so unlike RStanArm, where there's a few different choices for the families of priors that you can use, like, you know, Gaussian and Finnish horseshoe and all that, you have to use the same family in RStanArm for all the coefficients in the regression model. With BRM, if you want to, you can use different families for different coefficients, put different you know, prior information about those that don't necessarily come from the same family. And by default, if you just specify the class argument as B and leave the CoF thing blank, then it's interpreted as pertaining independently to each of the coefficients in the model. But if you specify CoF, then you're saying, okay, this prior pertains to a particular coefficient. And I think if class is something else, but there are more than one parameter in that class for the model that you're estimating, you can still specify the CoF argument to indicate which of those things you want your prior to pertain to, even if it's not strictly speaking a coefficient. Could be a standard deviation or something else. Group is the name of the grouping factor. We'll talk about this more when we get into multi-level models, which BRM is more than capable of estimating. Resp is the name of the response variable. So far we've only talked about models with a single outcome variable, more or less. Like when we did bowling, it kind of has two outcomes. But anyway, there are some models that can be estimated by BRM where you have multiple outcome variables or a set of outcome variables, and you're estimating the parameters for each of those outcome variables simultaneously, which is the Bayesian way to do it. But in that case, you need to specify the resp argument to the set prior function to indicate which outcome variable are you talking about when you refer to priors on the coefficients. But what we're going to do today and what we've done so far are just models that have one outcome variable, in which case the resp argument is not needed. We have the dpar argument for estimating so-called distributional models, which may seem kind of redundant because all models are pertaining to distributions of things. But distributional models, the phrase basically refers to models where that are different from the models that we've been talking about previously, where we sort of have eta be like a function of x's and coefficients and things like that. In so-called distributional models, you could also have sigma, the standard deviation of the errors, be a function of predictors that has its own inverse link function. If in the case of sigma, which has to be positive, that would generally be an exponential inverse link function. There's maybe a few other possibilities, but particularly in the Bayesian approach to things, you can have a different sigma for each observation. You can have those different sigmas be some generalized linear function of predictors that differ from one observation to the next, or one group of observations to the next. So this isn't something that is really supported by the functions in rstan arm, except for a little bit with the beta likelihood. But for the most part, rstan arm doesn't currently do this, but you can do things like this in brms. And so allowing for different error standard deviations as a function of the predictors, in which case you're estimating a so-called distributional model, and the dpar argument can be used to say, okay, this is referring to the coefficients in the part of the model that models sigma. And so in that, a model like that, sigma would be an endogenous unknown as opposed to exogenous unknown, the way we've mostly been treating it so far. LB and UB, lower and upper bounds on the parameters, usually not necessary, usually not advised to change those. If you're, if you have a model that has like sigma as a standard deviation in it, it's automatically going to be constrained to be positive, so you don't have to specify LB equals 0. But you can, if you want to, like specify a coefficient has to be negative, in which case you would put a UB upper bound of 0 and lower bound of like negative infinity or something like that. Or those bounds could be finite. But in that case, you need to be specifying a prior that is appropriate for the parameter space that you're using for those parameters. And then check, by default is true, tries to check whether the prior you're specifying is valid. You can get around the error message sometimes by specifying check equal false. So there's some things that are actually valid in Stan that BRMS doesn't know about. But more than often, if BRMS is telling you you have a mistake, you actually do. But there's also some things that you can get past BRMS that aren't actually valid syntax if you sort of go off on your own a little bit, in which case you'll get the error down the line. So we'll do an example of this on the next couple of slides, but any questions about these arguments to the set prior function? There's also just a little bit more convenient, just a regular function called prior, in which case the first argument doesn't have to be a string. They can just be expressions that are coerced into strings internally. The rest of the arguments here are the same. Questions about what any of those are doing? Yes.
Can I just clarify what you just said about the string versus prior? Oh,
yeah. Could you clarify if you wanted to assign different prior distributions to different coefficients in the model? Maybe you're about to tell us how to do that, but that might be helpful for the homework.
Yes. So each element, you can call set prior multiple times and concatenate the whole thing into a list. So if you had like two coefficients, you might, and you wanted to put different families of priors on them, you could call like prior, normal 0, 5, class equal B, coefficient age, all in quotation marks. And then, save that or assign it to our object. Then call set prior again, prior equal Cauchy 1, 2, class equal B, coef equal income. And then just make those all into a list and then pass it all to the prior argument on BRM. And so when you call set prior, the first argument has to be a string. If you just call the prior function, it's the same, except the first argument can be an expression rather than a quoted string, and it gets made into a quoted string internally. And I will show you how to do that. But If you want to call it for like one coefficient at a time, you just make multiple calls to set prior and keep track of everything in a list. Okay, so there are some defaults in what BRM is using. These defaults can be quite different from the defaults used in RStanArm, and that goes back to the fact that there's a finite, kind of large but finite set of models that are written by hand, and priors that go with them. And because we know what the stand program pertains to, we can choose more reasonable defaults, or ones that are known to work. Maybe not reasonable in any particular circumstance, but default priors that are known to work well across a wide variety of data that could be passed to that function in RStanArm. With BRM, like I said at the beginning, it's entirely possible that no one has used this combination of priors with this likelihood and data that are of this type, etc. And so it's less clear what would be good values of for defaults for those priors. But it should be clear what those defaults are just by calling the get_prior function, which will return back a glorified list of what BRMS will use for priors if you don't intervene by calling set prior yourself. And so get prior takes the same syntax as BRM does. So this is the syntax for a duration model where sort of time until death is a function of the age, the gender of the person, and what disease they have in their kidneys. Data equal kidney, family equal log normal. Okay, that's just specifying what the model would be. And then it comes back this list that has a print method that formats it like this as to what are the different parameters and what is their default prior. So you can see here immediately that by default in BRMS, the prior on regression coefficients is an improper one. Or more colloquially speaking, there is no prior on them, which is to say every value on the real number line is just as plausible a priori. That is not something that you should use, even though it's the default. It's pretty hard in general to come up with what would be a good prior for these coefficients. But anyway, it's telling you there's a coefficient on age, there's a coefficient on the interaction between age and female, there's coefficients for each of the levels of this categorical variable disease, and then there's a coefficient for female among someone whose age is 0. And then there's a intercept parameter, which actually does have a default prior, student T, scale degrees of freedom 3, scale of 4, or degrees of freedom 3, location 4, scale of 10. That's what's indicated here. So if you didn't put some other prior on the intercept, that's what it would use. So student T with 3 degrees of freedom is going to have heavy tails, but it's going to have a finite mean and variance. And that mean would be 4. The variance is not 10, but 10 is the scale parameter. So in a student T distribution, the scale parameter is not quite a standard deviation. But anyway, that is the prior that it would use by default. In a model like this, that may very well be too wide. Hard to say without knowing substantively something about what are the variables that are going into a model like this. Finally, there's going to be another standard sigma, which is the standard deviation of the errors in a log normal model, which again is not actually a standard deviation. So standard deviation of the log errors But anyway, that would also be student T, 3 with a location of 0 and a scale of 10. But since sigma is constrained to be positive already, this you should interpret as a folded T or a half T distribution, because negative values are already precluded by the fact that this is a sigma scale parameter for the errors. So by default, we have improper priors on the coefficients, a heavy-tailed but pretty vague prior on the intercept, and a heavy-tailed but restricted to be positive prior on the sigma parameter. So you would need to go in and specify something proper, or you should specify something proper for the coefficients, and you may want to pull in, specify a more informative prior for the intercept or the sigma parameter, depending on your understanding of the data generating process going in. But for any model that you can estimate by BRMS or by BRM function in the BRMS package, you can figure out what the default priors would be just by putting in like the first 3 arguments. But just because you can do that for any model, it'll tell you what it's going to use if you don't, specify it with set prior. But these things you shouldn't interpret as some human said they were a good idea. They may very well not be for the particular variables that you're putting into this model. Some thought were put into some of these, and a lot of times, people can get away with putting improper priors on the coefficients. That doesn't mean you should. But in other circumstances, with like the sigma parameter, when things really go wrong, if someone were trying to put an improper prior there, it'll come up with something. But that doesn't mean that this is going to be reasonable. So one, you should specify proper priors and informative priors generally, but you should also call the model once with sample prior equal only, just to get draws from the prior distribution and then make predictions from that to make sure everything is all reasonable before you go about trying to get the posterior distribution conditional on data that you've collected. So questions about using the get prior function. So this can be a much bigger structure because you can easily have models that have way more parameters than this, and in principle you could specify the prior on them one at a time, one parameter at a time, or as groups. Other questions about that? Okay. So the class argument, like I said, by default is B, which means it's referring to the coefficients, specifically what it refers to as population level coefficients. But that distinction between population level and group level is only going to make sense when we get into hierarchical models next week, and even then it might not make sense. But other possible values you could put in are things like intercept or sigma, and whatever is in the class column of the get prior function, you could specify as the class argument to set prior. And so to almost answer Nora's question, when we do something like this, we can call prior or set prior. In this case, I'm doing Cauchy median of 0, scale of 1, class equal B to say this pertains to all of each of the regression coefficients in my model, and I can save the result of that and then pass it to BRM. If I wanted to do different priors on different coefficients, I could by specifying the additional coef argument, and then I would need to bundle together those different calls to set prior into a list before passing it along to BRM. Questions about that? No? Yep.
you say again how you would specify different priors, different parameters?
Yeah, so again, this is going to involve the coef argument. So it'd be like coef equal female, and then I would, do something different. And so it would be like my prior 1, whatever, my prior 2, my prior 3. And then I think you have to put each of those into a list. So it'd be like my prior list is list, prior 1, prior 2, prior 3. Pass that whole list to BRM when you call the. So this, like I said, pertains to a survival model or duration model. These things are very common in public health, biostatistics, etc., where the outcome variable is almost always the amount of time until someone dies. But one of the things that people who do public health research and things like that, when there's studies, they have the annoying fact that they almost always have to deal with, that not everyone who is in the study is dead by the time the study runs out of money. And so you have people who are not dead yet, which more politely speaking are referred to observations that are censored, which just means they lived up until this amount of time at which the study was concluded, as opposed to everyone else, in which case their time of death is recorded as the outcome variable being modeled. And then we have a bunch of predictors, potentially, interactions between age and gender and what disease you have, what medications you're taking, all sorts of other things that might predict how long someone with kidney failure lives, starting from whenever you start counting, which is usually pretty arbitrary. And so these public health studies will almost always have censoring at the top end, but you can also have censoring at the low end, where you might start observing someone and let's say you don't know how long they've had the disease. You just know when you first observe them, they had the disease. Or you can get interval censored data where it's like the thing was between here and there, but you don't know the exact point. All of those can be handled with BRM and other software. BRM is obviously going to do this from a Bayesian perspective, but with survival models, you almost always have censoring at the top end, which needs to be taken into account. Now, biostatisticians know they have to do this, but there's a lot of people in econ and other things in social science that are like, oh, income was top coded. We saw that in one of the homeworks with the census data. That is an example where the right way to do it would be to indicate the censoring at the top end. We just did what a lot of people would do for that homework, which is wrong, which is pretend those top coded numbers are actual numbers rather than indicating the true value of income was greater than 500,000. Same sort of thing with these censoring in public health models where somebody lived to the end of the study, but because the study ran out of money at that point, you don't actually know literally how long they lived after that. And so that is information that needs to be conditioned on, taken into account when doing a model like this. So how would this look with a data generating process that has censoring? This is an example of a STAN program to draw from the prior predictive distribution of a model like this. So we're going to return an S by N matrix of prior predictions. So it's going to take S, the number of simulations we want to do, a few thousand, vectors for the prior location and prior scale on the parameters in the model, a vector X of predictors. I could do this with more than one predictor if I wanted to, and another exogenous known thing, which I call end, the time at which the study ended or is going to end, which marks the demarcation between times that are observed exactly and times that are censored, in which case you just know that it was like more than this. So we take n from the number of rows in X, set up a matrix for prior predictions called out, which is S by n. We create, which is usual in a Bayesian context, centering the predictors by subtracting the mean. Then we drop into the loop over the number of simulations. At each iteration of the loop, we draw from the prior distribution. So first we're drawing from our prior distribution on the intercept, alpha, which for sake of example, I'll use Cauchy here with the median given by the first element of log and scale given by the first element of scale. Do the same thing for the coefficient, except now its prior location is given by the second element of log in the second scale. So even though I only have one X in this particular prior predictive distribution, you can see how you might pass a vector of hyperparameters, and so you could easily extend this to having more than one predictor, which is like what we'll do here in a second. Also draw from the prior distribution of the standard deviation of the log errors using, for example, an exponential distribution. So RCNRM tends to use exponentials for things like sigma, whereas BRMS tends to use half T distributions with low degrees of freedom. That's just the way it is. Anyway, so that differs from what BRMS would do, but it's something that you could specify if you wanted to in set prior. So given my alpha and my beta, I can create a linear predictor, eta, by just multiplying my centered X by a slope and then shifting it over by a realization of the intercept. I then drop into my loop over the number of observations. So I'm going to fill in the sth row of my matrix of prior predictive realizations. And so inside the loop, I'm going to take a realization from a log normal distribution, which is to say take a realization from the normal and then anti-log it. There's actually already a log normal distribution in Stan, so you could just call log normal if you wanted to, but this is equivalent to that using the nth value of the linear predictor and the realization of sigma that I obtained before for the standard deviation of the log errors. I anti-log that up to get a positive value for time. This is the actual prior predictive value of survival time. But I know because my study has an end date of December 31st, 2019, that if anybody is still alive then, they're just going to get recorded in the data as still alive as of the end of 2019, not knowing exactly what time it is they died. And so when it comes to the prior predictive mechanism, I'm going to use the ternary operator, which is the same as in C++. This is basically how you do if-else in the Stan language. So you evaluate whether t is less than the known value end, which is when your study is going to end. If so, then my prior prediction for that observation is just t. But if t is greater than or equal to end, then it's just recorded in the prior predictions as you survived to the end of 2019. And so whatever is the end date of the study is what's going to be recorded as your outcome variable, even though such a person is being predicted to actually survive into 2020. We just don't know exactly how long they have left. And then when we're done with both loops, we just return the matrix of prior predictions. So this is an example of a data generating process with a censoring mechanism. You can have different censoring times for different individuals if they sort of come into the study not all at once, or other reasons why you might want to have a vector of n times rather than a scalar n, but this is a more simple version. In any event, in this particular model, we know the end time of the study. So that's an exogenous known. In other more sophisticated models, you might have censoring or some sort of truncation going on, but you don't know exactly what point that happens, in which case the censoring point becomes an exogenous unknown, or maybe even an endogenous unknown if you have some sort of a model for it, but you don't know exactly what it is. Similar sort of data generating process in a situation like that. Questions about this, what's being assumed by this censoring model here? So we're not going to have time to talk about something like this today, but if we were to write the kernel function that would go along with this, basically it's a lot of the same things that we've seen before. If someone's time of death is before the end time, then it's just sort of a regular log normal likelihood contribution for those people. But if someone survives to the end of the study, then we don't know exactly what time they died. We only know it was greater than whatever end is. And so for those people, we need to either model their time of death as a missing value, which we'll learn how to do like the last week of April, or what brms is actually going to do is put an additional contribution to the log likelihood, which is the logarithm of 1 minus the CDF evaluated at the end time. So the logarithm of 1 minus the probability, or 1 minus the probability at the end time is literally the probability that you survive past the end of the study. So the logarithm of that probability, 1 minus the CDF, is an additional term that gets added on to the log likelihood for a model like this. And then you can sort of posterior predict the actual survival time of the people who were censored in your data. Anyway, so that's what BRM is doing in a model like this. We'll learn how to do it ourselves at some point. Anyway, here's how you call BRM, which is like, after having done all that, a relatively simple thing. The same stuff that you would have given to get prior, but now you're specifying prior equal my prior, you know, whatever that list of stuff is, characterizing your priors on the coefficients and the other things. You get back output that is fairly similar to what you see with RStan ARM, maybe a little bit different names. So here we have estimate, that's actually posterior mean, and estimated error, I don't like that, but it's posterior standard deviation. Again, Paul is coming from psychology, and that's a field that is overwhelmingly not Bayesian. There are some people doing some Bayesian stuff, and they tend to be the better applied researchers in psychology, but for the most part, historically, at least since like the 1950s or so, it's very frequentist. And so instead of putting like mean, standard deviation, the headers of these things are sort of intended to not set off alarm bells by people who are just looking at the results and thinking this is some sort of frequentist output. Lower bound and upper bound on credible intervals indicated CI so that people think they're confidence intervals, but they're not. Effective sample size, which is pretty good in this case, R hat, which is close to 1. It's not a great measure of convergence, but it's the one that's being reported currently. So those are the sort of the summary on all of the coefficients. There's also a posterior distribution on sigma, which is the standard deviation of the log errors. Now, again, just like with BRMS, or just like with RSTAN-ARM, you're not restricted to just what the summary output says. You can do stuff on the whole matrix of draws from the posterior distribution. This is just intended to give you a quick overview of some aspects of the posterior distribution, and to be able to show something to people who only want to look at frequentist results for no particular reason. But you should not restrict yourself to just what the print output comes up as. Another thing that's in BRMS, it's not in RSTAN-ARM, although you could do this yourself if you access the underlying matrix of draws, is the hypothesis function, where you basically give it the thing that you just estimated in a string indicating your hypothesis, which is usually going to be something is greater than something or something is less than something else. It will basically just calculate the proportion of draws that satisfy that condition and report it as a probability, which is just like a posterior probability that the coefficient on disease, I don't know what GN stands for, but some sort of kidney disease, your hypothesis that is negative, indicating you're more likely to survive less time if you have that disease. So that seems like kind of a reasonable scientific hypothesis. I'm not such a fan of naming the function hypothesis because it's like easily misinterpreted as you're testing like a point null hypothesis. Really, in this case, you're not testing, you're just evaluating like what's the probability the coefficient on this disease is negative, and you get back a probability of that. Finally, there's 75 or other some odd functions that you can call on the result of BRM, the list that comes out of that. Many of these are the same or analogous to the same functions that you would use on an object produced by something in RSTAN-ARM, but like as matrix, as data frame, you can calculate the Bayesian R squared. You can call bridge sampler if you want to do base factor stuff. You can call launch shiny stand if you want to investigate the graphical stuff. All these LU things that we talked about with RSTAN-ARM, you can do those as well. There's a few other things that we haven't talked about yet that you could do with RSTAN-ARM or BRMS. You can do these posterior predictive checks with the PP check function, much the same way that you would do it with RSTAN-ARM. You could get posterior linpred, posterior predict, they're in there somewhere. Residuals, all kinds of other things like that. It has an update function where you can change, some of the arguments to an existing call to BRM and then estimate the thing again. So all of these sorts of things you can do. Many of these are the same as you could do with RSTAN-ARM, and then there's a few more. We'll talk about some of those additional ones on Thursday. Talk about ordinal models, talk about some nonlinear models that you can do with BRM. And then we'll come back to BRM a couple weeks after that when we start doing multi-level models. Okay, so that's it for today. See you on Thursday.